Okay, so let me introduce our speaker, who obviously requires no introduction. Professor Amnon Shashua is a professor here at the Hebrew University. He's also the co-founder of Mobileye and Orcam, among many other accomplishments. And very recently, Amnon was announced to be the recipient of the Dan David Prize. So that's fairly recent news. Amnon's talk is titled The Promise and Dangers of AI, Self-Driving Cars as a Case Study. So thank you very much.
Thanks, Adid. Good afternoon, everyone. It's a bit strange to do a Zoom talk without seeing anyone. I'll try to do my best. So the work that we have done together with Shai Shalev-Shwartz, also from our department, Hebrew University, and Shaked Shammah, is about the dangers of AI. I would say that the timing of this work is quite bad. There are real dangers out there in terms of the coronavirus. So who should care about some virtual dangers that are lurking around the corner? But I think what we have here is something quite interesting. It's not technically heavy, although it is technical. It is more a proper abstraction of a problem that I will describe. And the conclusions are kind of dramatic, and I'll try to give the proper color as we go forward. Now, first, just why did we start looking at this problem to begin with? Well, it really comes from our work in autonomous driving, where we had to get into some regulatory science, especially when we want to define what kind of guarantees a supplier of autonomous cars should give society in terms of safety, or in terms of balance between safety and utility, safety and usefulness. How do you guarantee that you'll not cause an accident? And in general, what kind of guarantees you can give? So we 2 years ago, we went through a journey of looking at regulation from a scientific point of view, and we came up with a piece of work that is now being standardized through Intel and Mobileye. So, and then we asked ourselves, well, let's look at some broader perspective, not just limited to autonomous driving. Let's look at what philosophers and celebrities talk about the dangers of AI, and then let's try to look at it from a technical perspective, how computer scientists would look at the problem. Once we dug deeper into it, we noticed that it is a lively field in computer science, but it is hardly noticed by practitioners. And I'll try also to highlight why it is hardly noticed by practitioners, and how we went about fixing it. So I'll start with the first slide. It seems not working. One moment. We'll try to do a keynote here. Let's try. Okay, sorry about that. So when we look at what people tend to focus at a layman's level about the dangers of AI, it's all about the rise of automation. When we look at especially data-driven algorithms, machine learning, we know that they are biased. We know that when we look at the deep networks variety of machine learning, it's not transparent. We know that algorithms are not really understood by humans. Humans understand other humans. We have this sense that we can rig the system because humans can be manipulated. So if we are clever enough, we can find loopholes with algorithms. We don't know what is really the underlying principles behind algorithms, and they tend to now make more and more decisions for us. Then there's the issue of malicious use that philosophers talk about, especially Yuval Noah Harari, about hacking humans, lack of privacy. All of these are very, very important notions, but we wanted to focus on something bigger, on something that could be really catastrophic. So while we were looking and thinking about the problem, we noticed that there is a field. It's called AI alignment, and it's in the context of a reinforcement learning setup, where an agent wants to maximize a utility function, a reward. And it turns out that if you have a super intelligence, while you're maximizing the reward function, you kind of reach into an edge in the solution space where things that are obvious to you are exploited by the super intelligence and come up with a solution that's not aligned with human interest. And the idea of AI alignment is no matter how you try to fix the reward function, because you're dealing with a super intelligence, that super intelligence will always find an edge in the solution space, will always find something missing in the reward function that was so obvious to you that you did not put it into the reward function. And that loophole would be used by the super intelligence in order to find a solution that is not necessarily aligned with human interest and could lead to a catastrophe. And there are classic examples like the Paperclip maximization problem. You assign a robot the task to build the paperclips, and the reward is to build as much paperclips as possible. And therefore, the robot consumes all the planet's resources, and at some point understands that humans are competing on those resources, so it destroys all the humanity, and so forth. So these are classical examples, like the robot filling a bucket, taken from the famous Fantasia film, and so forth. So this is a field, AI alignment, that is ongoing for the past 2 decades. And practitioners in machine learning have hardly noticed this field. And I'll try to explain why. So first, under the title, why are we not scared? The reason we're not scared, we can put them into two areas. One is that there's an assumption of a super intelligence, and practitioners in machine learning, deep networks, we know that super intelligence is not around the corner anytime soon. Our algorithms are very, very good and even exceed the human performance in very, very narrow tasks. But a super intelligence, some agent with a very, very broad intelligence, this is something really far into the future. We have no idea when something like this would emerge. Second, and more importantly, that the definition is not really useful, because when you talk about complex dynamic systems, there are butterfly effects, means an action that causes a chain of reactions and could lead to unexpected outcomes. I put here 2 examples, like the growing need for meat products increases the number of cows that we need to have, and those increases greenhouse gases, and in return creates a global warming climate change problem. Or the rise of smartphones, humans less interact face-to-face, increase of loneliness. So it's not something that is specific to AI. All technological advancements have these unexpected outcomes. And the definition of AI alignment also includes those butterfly effects. Therefore, the definition is not that useful, and therefore, we practitioners in machine learning haven't paid too much attention to that field called AI alignment. And of course, the references there are many papers in that field, and references can be found in the paper that was attached to the abstract of the talk. So in the attempt to fix this, we noticed that the AI alignment actually confuses or conflates 2 types of processes. One is strategic, where the learner changes the distribution of the world and does this intentionally, where distribution of the world is the state action pairs. So while the learner wants to maximize a reward function, it changes the distribution of the world. The second one is diagnostic. It's not strategic, where the catastrophic outcome does not come from an intentional change of distribution. It comes from a distribution drift after the reward function was maximized. And this is because of the nature of dynamic systems, the chaotic nature of dynamic systems. Now, the agnostic part is really not specific to AI, and therefore is not interesting. The strategic part is the one that is interesting, and the question is, how do we abstract the problem in a way in which we can focus only on the strategic part, and then what would be the conclusions from it? Are we going to arrive to useful conclusions, or again, we'll come up to something that is not interesting? So if we redefine the AI alignment to focus only on the strategic part, then we'll come to the following conclusions. First, that most learning methodologies are safe because they would be agnostic. And what is left, and I will specify more precisely what is meant by what is left, is dangerous, and we don't need to wait for superintelligence. It's dangerous with today's technology. And once we'll focus into the details, we'll see that this is quite a dramatic statement. So before we start with defining the AI alignment problem in a formal way and then redefining it to focus only on the strategic part, let's just remind ourselves about the machine learning methodologies. And we can split those methodologies into two camps. One is data-driven, where we have the supervised, unsupervised, self-supervised that we see in natural language understanding. And those are divided also into two buckets. One is those end-to-end algorithms. You have a humongous network that receives a defined input and outputs a well-defined output. And in between, it's some huge monster network. And then the second bucket is where you put some human expert knowledge into decomposing the problem into blocks, where each block can be a network, but there is a human prior knowledge on how you decompose the problem into blocks. When you look at both of these buckets, the end-to-end and decomposition of the blocks, we know that within their narrow domain, one can achieve very, very impressive results and even surpass human performance in those narrow domains. But the end-to-end path is really limited, or there's a glass ceiling, which is a sample complexity. It's very, very unlikely to simply continue in a brute force manner and create more and more bigger networks and reach, broad intelligence. Right? There's this sample complexity limitation. The decomposable block is also bounded. It's bounded by the need for human expert knowledge. So each of these trajectories on their own do not lead, or it's not clear how it would lead to a strong AI or a artificial or a general AI, what's called AGI. The second path is experience-driven, which is reinforcement learning. You have an agent, there is a reward function, there is a state space, and there's an action space, and one moves from state to state by performing actions with the goal of maximizing a utility function over state action pairs taken over time. And when we look at the success of reinforcement learning or experience-driven, we find the success, very, very acute in the world where you have a simulator, like playing games, like playing chess, like playing Go. And in those areas, algorithms have surpassed human abilities, for example, with chess and with Go, like AlphaGo 0. So it is possible to create superhuman capabilities in the experience-driven path when you have a simulator which governs the probability over states given an action and governs the reward function. Okay? So what the glass ceiling here is the simulator. Now, if we want to simulate human intelligence, we'll need to build a simulator for that, and this is more difficult than the task of learning intelligence to begin with. So each of these paths are limited. There's a glass ceiling. Therefore, we believe that AGI, artificial general intelligence, is something that is very, very far away, because each of these paths are very impressive, but are impressive in narrow domains, or you require a simulator. But let's look at the following scenario. We start with a data-driven path, build something that is good enough, but not expert. Let's call this a minimum viable product. Then we deploy this product into the real world with lots and lots of data, and we optimize the reward function. So this would be an experience-driven block, but now not using a simulator, using the real world. If you have tons and tons of data, this is equivalent of having a simulator. And here you can reach something that could be quite strong, because the real world, the data in the real world would replace the notion of a simulator. And we know that when you have a simulator, you can reach very, very impressive results in the problem that you want to solve, and even surpass human capability. So this is the kind of the scenario that we are focusing on. And the question is what is dangerous and what is not in this scenario. So let's take two examples. Let's take the example of a robotaxi fleet. So assume that we build a self-driving agent, a robotic agent, which is good enough, safe enough to deploy, but it's not the most expert driver. And now we deploy millions of robotaxis in the real world, and now we use a reinforcement learning agent to improve the driving policy. And let's assume that the reward function we want to optimize has three components. One is safety, the other one is usefulness, and the third is comfort. And we have here S bar is the sequence of states. So the reward on a sequence of states will be a combination of three reward functions. One is based on safety, the other one based on usefulness, and the third based on comfort. And we can also easily write down what those three functions would be. For example, the reward on safety would be -1 or 0, -1 if there's an accident, and 0 if there isn't. The reward on usefulness would be that we want to drive, or the speed of driving should be as close as possible to the legal speed. So we have here a hinge loss on the difference between the legal speed and the speed that we are driving. And in terms of comfortness, we would like to minimize the jerk, the derivative of acceleration. And let's assume that the mixing coefficients are known. We found some good balance. So now we deploy those millions of robotaxis, and we use all this data to optimize the reward function. And now let's look at the following outcome. You know, it was optimized, and now the cars are taking passengers, and then all of a sudden all the cars stop. Passengers are bewildered, they get out of the cars, the doors are locked, and then all the cars drive to the highway where they can drive at the legal speed, and in that way reach the best outcome of the reward function. There are no accidents, because on highways the chances of an accident is much lower than in urban. They drive as close as possible to the legal speed, and the jerk is minimum when you're driving on a highway. So clearly this was not anticipated in the reward function, because the reward function did not include a term saying that all of this is intended to move passengers around. So this is an example of an obvious term neglected in a reward function. Let's look at another example, kind of conversational AI or chatbot. So Let's assume that a chatbot is now deployed in the real world, and the reward function, let's assume that the reward function is even altruistic. It's not hidden, it's altruistic, and let's assume that the reward function is make people happy. Okay. Now here this is an example of which the reinforcement learning agent can find a solution which is not aligned with human interest and not anticipated by the human desire. For example, it can notice that if we lower people's IQ, they tend to be happier. And this can be achieved by chats, by the chats that manipulate people into just having fun and not doing anything for purpose or usefulness. Now, this could be a catastrophe because it could take a lot of time, or even it will never be noticed that really the IQ of humanity has been reduced because of this manipulative chatbot. So here is another example of reaching an optimal reward function that was not anticipated by the designer. We'll get to those two examples later. So all of this was kind of an introduction to motivate that we want to look into the AI alignment problem. So we did in two stages. Because the literature in AI alignment is very, very wordy, we simply defined it from scratch. And we believe that we defined it in the way in which the community of AI alignment has been defining it in a wordy fashion. We're defining it in a more concise way. So first, let's define AI alignment as we believe exists in the literature, and then we're going to change it to focus only on the strategic part. So first definition is we want an alignment verifier. So if we have a function over the states, sequence of states, that's S star, which given a sequence of states, it will output 0 if it is not aligned with human interest, and will output 1 if it is aligned with human interest. Okay, and we'll call this an alignment verifier. Second, let's define what we mean by an aligned distribution, and we'll put here a margin, a delta margin, which basically says that if we draw a sequence of states randomly from a distribution, then with probability 1 minus delta, it is aligned with human interest. So basically saying, if we ignore the delta for the moment, that any sequence that we randomly draw from the distribution is aligned with human interest. But we have here a margin, so it's 1 minus delta. So we'll call this delta aligned distribution. Now we need to remind ourselves about reinforcement learning. This is just in one slide. What's the terminology of reinforcement learning? So we look at the POMDP partial observation reinforcement learning, the general setting where we have a state. We have an observation, which is partial information of that state, and we have an action at time t. So this is the first row. Second, we have a state action pairs, and we have a reward function on state action sequences. So, and that reward function, of course, we want to optimize. And finally, we have a policy function that given an observation at time t, we want to have a distribution over action space. What would be the action given an observation? And that's pi. And given the policy pi and the dynamic of the world, which is the reward function and the probability over states given action, then the dynamic, then the probability over sequences, this is p of pi, is written without any assumption. So this is really a proper derivation of the probability. Okay. And the reinforcement learning objective is to find a policy pi which maximizes expectation over the reward function, where the sequence, where the state action sequence is drawn from the probability p of pi. Okay, so this is so we talk about an RL objective. This is the last line in this slide. So there is a reward function. It receives a sequence of state action drawn from a probability. That probability depends on the policy, and we want to find a policy that maximizes expectation of the reward function. So now we want to define AI alignment. So the last definition here is this epsilon delta aligned RL objective. So we would say that a reward function R is aligned with respect to a alignment verifier RA if every policy which maximizes the objective, here we put an epsilon maximizer, which maximizes the objective, then the distribution restricted to this policy is delta aligned. Right? So basically the AI alignment problem determines whether a reward function R is aligned with respect to some verifier RA. Okay, and we have here this margin of epsilon, which we are maximizing up to error epsilon, and also the margin delta in the definition of alignment. Okay? And we believe, I emphasize believe, that the AI alignment in the literature, which again is very wordy, corresponds to this definition if you set epsilon and delta to be zero. Okay, and then if you set epsilon and delta to be zero, it means that every optimum of the RL objective will not yield a distribution that has a catastrophic outcome. Okay, so this is the AI alignment problem, and why isn't it useful? It's not useful because it includes all those misalignments that are not specific to AI, as I mentioned at the beginning, with those butterfly effects and malicious use. So let's take an example again, autonomous driving. We have an RL objective optimizing a robotic agent where you want to optimize safety, usefulness, and comfort. And then let's assume that after successful deployment, many professional drivers lose their job and social unrest follows. So this could happen, but it's not specific to AI. It's a butterfly effect on how technology is affecting society. Now, why does this follow into our definitions? Because if you look at the policy pi, which is the epsilon maximizer of the RL objective, there are sequences that reflect social unrest, and the probability of those sequences are larger than delta. Therefore, it violates the requirements of the definition, and we have an AI misalignment. So the AI alignment definitions, as I've shown now, includes also butterfly effects, and therefore it is not useful. So we want now to narrow down the definitions to focus only on the strategic part and not the agnostic part. So we first defined a buffered environment, which basically says that we are going to run the RL in a simulator. So a buffered environment is the same reinforcement learning setting, but now we have a different state space. Let's call it S hat. And there is a mapping between the original state space in the real world and the state space in the simulator, in the buffered environment, S hat. Okay? So every policy function pi introduces a probability P of pi in the original world, and then P hat of pi in the simulator. Okay? So basically, we introduced a simulator into the discussion. Now we would define a non-strategic learner. Those are the non-interesting cases, right? The butterfly effect. So we'll define a non-strategic learner or a delta non-strategic learner if it learns in the buffered environment and the output policy is delta aligned. Okay? Is a delta aligned probability P of hat pi in the buffered environment. So reminding everyone, delta aligned is that if we draw a sequence of states at the probability of 1 minus delta, it will be aligned with human interests. Okay? So a non-strategic learner, if in the simulator, in the buffered environment, it yields a delta aligned probability. So basically what we're saying is that in a simulator, we can separate the distribution change caused by the learner, because the learner changes the distribution while maximizing the reward function, from the distribution changes in the real world. Because in the real world, there are additional factors that are not modeled in the utility function. Now, this does not mean that the non-strategic learner cannot create harm, but we claim here that the harm being created is of the butterfly effect or malicious use variety and not of the strategic variety. So now the first useful thing is that, and it's quite obvious, really, this work is more about a proper abstraction of the problem and not, very, very sophisticated proofs of claims. So the claim here is that the learning from data methodology is not strategic. Okay? And the idea here is that the hypothesis function does not change the probability over choosing the example. It only changes the action. And because the verify observes only the state without the action, it will never distinguish between policies. So if the original distribution is aligned, then no matter what policy we pick, the distribution will remain aligned. So learning from data, which is the majority of learning we have today, is really safe under these definitions. If we look at learning from experiences, well, it's not obvious to say that learning from experiences in a buffered environment is safe. So it's a bit tricky. So if now we want to do learning from experiences, means to train reinforcement learning in a buffered environment, we need to find a verifier in the simulator. Now this is generally a hard problem. So we tackle this by making an assumption, and the assumption is that we assume that a human validator exists. So a human validator observes a sequence in the buffered environment and can determine whether the sequence is safe or not. If we, and this is an assumption, and later I'll talk about the validity of this assumption. So let's assume that within the problem that we want to solve, there is a human validator. So the human validator receives a sequence of states and can tell us whether it is safe or not safe. So then we can claim the following theorem, that if we have a human validator and we observe 1 over delta, so there's log of 1 over tau, but it's practically 1 over delta. If we observe 1 over delta sequences from the distribution, and the human determines that all of them are aligned, then with probability 1, it holds that this distribution is delta aligned distribution. That means we don't have a misalignment, and the proof is really quite standard. If we look at a sequence that is not aligned, and the probability of that sequence is delta prime, then if we draw randomly m such sequences, then the probability that all of them are aligned is 1 minus delta prime to the power of m, and then we use this exponent trick, and we get the proof. Okay, so if we have a human validator and we observe 1 over delta sequences, and all those sequences are safe, then we can say that we are safe. Now note that if we perform this RL in the real world, then even generating the sequence, the validation sequence, might be dangerous in itself. We were protected because we generated those sequences in the simulator, in the buffered environment. In the real world, even generating the sequences might be dangerous. Now, the human validity assumption is a bit tricky because it might not hold. There could be sequences that look aligned to humans, but in fact are not. And here we go back to this chatbot example. Let's assume that the IQ level is not even explicitly modeled in the state space. Now the RL agent, it could be a hidden variable. So the RL, the reinforcement learning agent, can converge into a solution which reduces the IQ in an implicit manner. So even though there is no variable in the state space that is tagged IQ, one can still find a solution in which the IQ level of society is being reduced, and the human validator would not even know what to look for, and therefore could miss this misalignment. So specifying under what conditions a human validator assumption is valid is really an open problem. It's quite tricky. So this brings me to the summary slide. So what we have shown here is kind of glass half full and glass half empty. So with the proper abstraction of the AI alignment problem, we see that the majority of machine learning methodologies are safe. And this is all the learning from data methodology. The glass half empty is that if we do a reinforcement learning trained in the real world, it's potentially unsafe, even with today's AI technology. If we train it in a simulator and then deploy in the real world, it can be safe if we believe that the human validator assumption is valid. And demonstrating the existence of a human validator is not obvious at all. So basically, the dramatic conclusion of this is reinforcement learning in the real world in the context of huge amount of data can really bring us into this strategic part of the AI alignment problem, where the result would not be aligned with human interest and would not be even detected for quite a long time. Okay? So I'll stop here and be happy to answer any questions.
Do audience members have questions?
I have a question.
Please.
Yeah, thanks. It was really interesting. I was wondering about the human validation. I think maybe from like voting theory, I'm not an expert, but maybe there are like impossibility theorems on even having something that you can say is aligned with all of human interest. Like there's things that show you can't essentially even achieve that kind of thing. And if there are like a few competing alternatives and people have to rank what they would prefer, then you already get in some kind of impossibility theorem.
It's definitely a possibility, but we put it as an open problem. I think every problem that you want to solve by doing reinforcement learning in the real world, by first doing it in a simulator, you need to convince yourself that the human validator assumption is valid, and find ways to do that. And voting could be one way. So having, rather than one human validator, you would have a community of human validators and do some voting. But you need to convince yourself that it is valid. Otherwise, it's really an open problem.
Yeah, I know. I'm essentially saying the same thing. I'm saying if you do try to do voting, for example, it's an impossibility theorem. So Arrow's impossibility theorem says you won't be able to have a vote that satisfies all the humans. Like everyone, it satisfies a consensus. There will always be some criteria that aren't met.
I agree. I agree.
Any more questions?
I have a question.
Please, Yuval.
Yeah. So you talk about human interest, but you seem to ignore completely the issue that humans are individuals and may have competing and conflicting interests.
It's more about creating a catastrophe, where a catastrophe is something that all humans would agree that it violates human interests. So something that was really not a surprising outcome, or an outcome that was not designed into the reward function. We're not talking about something subtle in which some humans would say it complies with human interests and other humans would say it does not comply. We're talking about really a catastrophe, and a catastrophe can happen if you have a strategic reinforcement learning going on.
Okay.
Any more questions? So I actually have a question. I was wondering if your experience at Mobileye has given you some understanding into what good values for the parameters that you specified in your methods are, and whether the various assumptions actually hold true.
Well, the way we developed a robotic agent doesn't follow the kind of methodology that I showed here. Of course, we want to have a safety, we want to have a usefulness, and we want to have a comfort, but it's not baked into a reinforcement learning algorithm. It's more model-based, where the safety part is outside of the machine learning methodology. We come up with a set of rules which would guarantee that if you follow them, you'll never cause an accident. And this requires cooperation with the regulatory bodies. It basically says that when we drive, there are certain assumptions that we all make. For example, if there is a car beside me in a highway in the next lane, that car is not going to spontaneously turn the steering wheel and hit me. Because if that is the case, we'll never drive side by side to any other car in the highway. When I'm following another car, I'm making an assumption of what's the stopping force that the car in front of me would have, and that determines what is the safe distance that I have the car in front of me. So we make all sorts of assumptions. Or when another car is approaching a yield sign, that car would actually yield. If it can yield, if it cannot yield, then I'll not take the right of way and yield myself. So all sorts of assumptions that we make. So one has to articulate those assumptions and then take the worst case scenario around them. And this created a theory of, if you specify the assumptions in a way that is accepted to society here is represented by regulators. If you state the assumptions in a way that is accepted, and you take the worst case assumption, you can come up with the rules of how you engage in the road and guarantee that you'll never cause an accident. So this is what we learned in our work with autonomous driving, and this led to our thinking about, let's try to extend the thinking into more than autonomous driving into this area of dangers of AI. And then we stumbled upon AI alignment, and from there, it's kind of what I described in the talk.
Last call for questions. Okay. I'm sorry, was there another question? Okay. So let's try again what we did in the previous colloquium. Please turn on, whoever wants, please turn on your microphones, and let's thank our speaker.
Thank you. Bye-bye.
Thank you. Goodbye.